Well, good afternoon, everybody. It's about 2 minutes after 2 o'clock, so we should get going. I think people are still drifting in, but we should maintain time. My name is Peter Irwin of RWDI, and my co-chair is Roy Danoon from CPP, and we have a good bunch of papers this afternoon. The first one is Professor Yukio Tamura on the aerodynamic behaviors of tall buildings and unconventional configurations. And I know that Dr. Tamura hardly needs any introduction. He's chairman of the International Association of Wind Engineering and has many other honors to his name. And we have some excellent material that I know he's going to present. So I'll hand over to Dr. Tamura.
Thank you very much. So I'll talk about the aerodynamic behaviors of tall buildings with unconventional configurations. So I already talked about this in some conferences, ASC or IABSE, but today I added some materials. As you know, recently many tall buildings with unconventional shape have been constructed, and many buildings are twisted, tilted, or inversely tapered. A lot of different types of building we have, but there are not so significant enough study on the aerodynamic behavior, especially the comprehensive study has not been made. So we did experiment for these 31 models in 7 categories. By using high frequency force balance technique and simultaneous pressure measuring system. As basic models, we tested 4 models, but basically we are interested in the square, but the rectangular, circular, elliptic shape is kind of reference. Especially circular elliptic, we should discuss the Reynolds number effect, so this is just for the reference. So height was set at 400 meter, all models are 400 meter, and volume was set as 1 million cubic meters. So these 2 conditions are always kept for different shape. So corner chamfered, corner cut, tilted or winding, and tapered model, 2 tapered, 4 tapered. 2 tapered becomes rectangular near the top, and setback inversely tapered and bouged. And helical models, different type twisting angle, 90 degree to 360 degree. And also 2 additional helical model, rectangular, elliptic. And different types of opening models, cross opening and oblique model opening with different opening ratio. And also we studied a composite type, a combination of corner cut and helical, corner cut tapered helical, and corner cut setback, and so forth. So we did not expect significant effects of the combination, but the result was different. So when the condition was set as here, as shown here, urban area was simulated, and this is an example of mean overturning moment coefficient for a long wind and crosswind. So as you know, that this should be a function or change with the wind direction. And in the left figure shows the long wind case, and the right is crosswind. And we picked up the one maximum value among all wind direction for each model. This is only the example for 6 models. And we compared the result. And this is also the part of the result. Only for 10 models we compared. So the left end is square. So if the value is lower than these 2 lines, the aerodynamic behavior is better than square. So corner cut, taper, setback, all models show better than square model, even for mean value. And we just changing the shape is aiming to minimize the crosswind force, but even for a long wind, the performance is good. And this is the fluctuating overturning moment coefficient for the same 10 models. So as you can see, almost all models performance is better than square. Especially the fluctuating component of crosswind, the significant reduction is made for composite model. So combined effect also significant. And this is the power spectrum of crosswind overturning moment. You can see the spiky peak for square model. And you can see some reduction of the peak due to different configuration. So incidentally, the 500-year recurrence wind speed level in Tokyo is almost close to the peak of the spectrum. So we compare the value of the peak, and also we are interested in the 1-year recurrence wind speed level because we in Japan we evaluate the habitability, human comfort for wind induced motion based on the 1-year recurrence acceleration. So we compare the value of the power spectrum of crosswind force. So for 500-year recurrence wind speed level, the all 9 models are better than square, and significant reduction is observed for composite model. The value is square of the reading of the peak, so the significant reduction is obtained for these 3 4-tapered helical and corner cut combination, setback and corner cut, and setback and 45-degree rotation. So this result is very good. But for 1-year recurrence wind speed level, the performance is not necessarily good, but not so significantly bad, but worse than square for some case. And this is overall comparison in terms of mean wind force along with a crosswind. Again, the left end is square. So you can see that the rectangular model or tilted or tapered, 2-tapered, and helical rectangular. This rectangular type is not so good for mean component. And crosswind also almost the same tendency. That you can see some correlation between along wind and crosswind in mean wind force components. This is interesting. And for fluctuating component, also you can see the rectangular is not so good, and inversely tapered and tilted is not so good. But other models show better result than square model, especially for crosswind. And also you can see some correlation between along wind and crosswind fluctuating component. And this is the peak value of the crosswind force spectrum for 500-year recurrence level. So again, the tilted and the inversely tapered is not so good, but other is good. Especially helical model and composite model showed a very good result. But for 1-year recurrence, as we already seen that some model is not so good, but helical and the composite showed a very good result. And this is overall comparison of the mean component and fluctuating component and peak value of crosswind force spectrum. I selected only the top 6 from in each category, but you please see the composite type, especially for fluctuating component and peak value of the spectrum of crosswind force. The top 3, best 3 is from composite type. So composite type is very good. So this is a correlation between along wind mean and crosswind mean overturning moment coefficient. As already seen that some correlation we observe. Not so clear, but some correlation we can observe. And this is the relation between along wind and fluctuating component and crosswind fluctuating component. So also they have correlation, high correlation. But more clearly, along wind component, fluctuating component and mean component show very good high correlation, suggesting the quasi-steady assumption. And also between fluctuating component and mean component for crosswind, In this case, correlation is not so high. Dispersion is very large because the source of fluctuation for crosswind is due to Kalman vortex, but mean component is different. So that is the reason. And the peak value of the spectrum and the mean value of the overturning moment coefficient for crosswind has shown such a scatter. So not so high correlation. But of course, fluctuating component of crosswind force and peak value of the spectrum show the high correlation, very high correlation. And this is the effect of the twisting angle on the mean overturning moment coefficient for any helical model. So you can see even for mean value, along with the crosswind show some reduction of the wind force due to twisting angle. More clearly, the crosswind fluctuating component show the reduction due to the twisting angle. And this is the variation of peak crosswind spectrum due to the increase of the twisting angle for helical model. So you can see very significant reduction of the peak value. And it reaches almost saturate from 180 degrees. So 270 degrees, 360 degrees is more than enough. And this is the variation of the bandwidth of the crosswind spectrum. Definition of bandwidth, we followed the definition by Professor Bicali for chimney. Based on that, the bandwidth increases with the increase of the twisting angle, and it reaches almost in the saturate from 180 degrees. So better situation had happened due to twisting angle. And this is the variation of the peak frequency due to Kalman vortex shedding at the local level from bottom to the top. So the square prism showed almost a constant frequency. So that suggests well-organized Kalman vortex shedding. But for setback or helical, show the change of the frequency from bottom to the top. So that suggests not well-organized Kalman vortex shedding happened. And this is also the similar result for composite type. More significant change of the frequency is observed for composite type. And a very interesting result is obtained for setback. Two different types of setback. Setback, ordinary setback, and the setback with rotation. So ordinary setback show some gradually changing situation or tendency of the frequency. That means upper part and lower parts affect each other. But in the case of setback with rotation, the frequency is clearly separated. So not correlated situation happen. So this is very interesting. And this is the change of the bandwidth of crosswind path spectrum. Helical, corner cut, and some composite type show the better result than the square. The wider broadband spectrum observed for such a configuration. So this is flow pattern of CFD to check the mechanism of the reduction of the crosswind force, but I cannot. I checked the video in the preparation room, but I could not make it. But you can see that well-organized vortex shedding from the square model, but the helical model, some very separated and dispersed situation observed. Sorry. Oh, it's working, but so next I will show some very briefly the combination of wind force. So this is a case of square model. So along wind and crosswind trajectory becomes like this, and along wind and the torsional moment, and the crosswind and torsional. As you know, the torsional moment and the crosswind, the source of the fluctuation are almost the same. Kalman vortex shedding is a main source. So these two are well correlated. So some positive slope they have, but these combination almost symmetric. That means no correlation. But when we look at the maximum value, such a wedge-shaped trajectory suggests the simultaneously occurring situation of the maximum crosswind and maximum alongwind. So that is a special feature for square model. But if you change the configuration, this is a corner cut, so such a situation disappear. And some still remain in this case, but helical model so becomes almost elliptic shape, and no correlation, of course, and no simultaneous happening of the maximum crosswind and maximum alongwind. So that is also another improvement of the aerodynamic behavior, the tall building model with different configuration. So maximum crosswind appear with almost average level of alongwind, and maximum alongwind appear with almost no zero value of crosswind. So such a combination is better than the square model. So this is just, we started the combination on the wind force components for different models. So in the future, we can discuss more detail about this. So this is just a trajectory I show. So this is a combination of alongwind and crosswind. I already picked up the combination of alongwind and crosswind. So wedge shape changes to elliptic shape, and also becomes more thinner and thinner due to the change of the shape. So ordinate indicates crosswind force. So if the trajectory is thin, that means the crosswind component is less than the square model. So this is the effect of twisting angle on the spectrum, and you can see that reduction due to the increase of helical twisting angle. And this is a result of the wind-induced response analysis for 500-year recurrence wind speed level. Blue indicates the maximum displacement and the story deformation angle. So I think it is better to compare, to look at the blue value. So all composite type and the helical model showed a very good result than square model. But for 1 year recurrence, peak acceleration, they're not necessarily better than square. So this should be careful in the design. Oh, okay, thank you very much. I'd like to conclude my presentation. Thank you.
Okay, that was a very good and very well-timed presentation.
Thank you very
So
much.
we have time for a couple of questions from the audience. If you've got a question, just stick your hand up and we'll get a microphone to you. Okay, I don't see any at the moment, so maybe I'll ask a first question. You obviously, Yukio, looked at a uniform height and a uniform floor area, which is all very nice if you have a nice open site. Have you looked at all yet at the case where you have a constrained footprint on a site? So therefore, if you change the shape, you can't change the footprint, so you change the height as a result.
Trajectory, right?
Yeah. So have you looked at the case where the height has to increase because you have a constrained footprint?
Yes, we did not check the different heights case, but the frequency can be different for the different shapes. So frequency effect appear in the response, but the trajectory only show the aerodynamic force component. So such an effect is not appearing. But we have not checked the effect of the.
Yeah. I believe we have another question from Dr. Irwin.
You showed some results for the 1 year return period and for 500-year return period. Now those results would depend on natural frequency.
Yes, that's right.
And on the wind climate.
Yeah,
so
yes.
My question is, how did you decide on those two aspects?
Yes, the figure I showed based on the same natural frequency. But later, some structure designer collaborated with us to calculate the natural frequency depending upon the structure model, FM model. So the frequency difference we have, but not so significant difference. So that preliminary study we set the same natural frequency. So, same reduced frequency is set at the 1 year recurrence and 500 year recurrence.
Just to continue though, you must have assumed the wind climate. Was that typical?
Yeah, yes, just only 500 year recurrence is based on typhoon record.
Okay.
But 1 year is a daily wind, basically, in Japan.
Okay, thank you.
Okay, if we have no further questions, we can just thank Professor Tamura
Thank you very much.
for a very interesting talk.